Hi, hello everyone. So far we have just discussed also that there is a limitation in electrical interconnect transmission line in integrated circuit. So it has a normally they use transmission line for electrical interconnect, and the transmission line that has a cutoff frequency, that means it is considered as a low pass filter. You cannot communicate high speed data. So optical interconnect came into pictures, and optical interconnect, the fundamental building block is electromagnetic, and that is optical waveguide. And optical waveguide, basically to understand optical waveguide, we have discussed a bit about electromagnetic theory, Maxwell's equation, plane wave propagation, etc. And now today we will be discussing about optical waveguiding. So electromagnetic wave in optical frequencies, if it is operating, then how to design optical waveguide. Normally we know that for higher frequency, relatively bit higher frequency, for example microwave waveguide, we use metal waveguides. Okay. So we would like to discuss first why the same metal waveguide cannot be used for optical waveguiding. So there will be some kind of limitations, and I will discuss that first, and then I will move on to actual waveguiding, different type of optical waveguiding and their properties in details. So let us start. You see, let us consider, to understand the optical waveguiding, we need to know how electromagnetic wave behaves in the interface between two medium. Two medium means, if I consider range of frequencies of operation you are considering in electromagnetic domain, electromagnetic wave. So you can think of that, okay, you have to deal with metal, dielectric, semiconductor, all those type of things. Here we are considering, for example, a reference frame here. For example, this is actually your medium 1, and this one below yz plane, in this figure below yz plane, we can this can be considered medium 2 according to this definition here, and this can be considered as a medium 1. And medium 1 is characterized by its parameters, electromagnetic parameters, that is permittivity epsilon and permeability mu 1, conductivity sigma 1. Similarly, medium 2, your permittivity epsilon 2, permeability mu 2 and conductivity sigma 2. We are just considering two medium characterized by these parameters, and they are meeting, this two medium meeting at x equal to 0, yz plane. That means yz plane you can consider infinitely extended, and for x greater than 0 you have medium 2, and x less than 0 you can consider medium 1. So exactly at x equal to 0 here, that is x equal to 0, you can consider that they are meeting, interface is there. And you can imagine that a electromagnetic wave propagating in medium 1 with a wave vector k I, okay, in this direction. Wave vector is a vector, of course, and it is propagating in this direction, and it is a plane wave you can consider. For example, if you can consider plane wave means, you can just consider something like this, maybe you can change the color. Yeah. So you can consider something like this. These are the plane waves, sorry. So parallel phase front, and you can say that this is your lambda. in that medium. So, if this is the plane waves making an incident at a normal, say consider here O origin here. This dashed line is the normal drawn perpendicular to the yz plane at O, and the wave vector making an angle with this normal is theta I. Then what happens in the interface? Normally, because medium is different, one medium is creating one type of impedance, second medium will be another type of impedance. So, there is an impedance mismatch. So, because of this impedance mismatch, fraction of the power or wave will be reflected back with an angle theta r, and rest it will be transmitted to medium 2, and corresponding your wave vectors are shown here kt and here kr. Okay. And also we can consider that since it is a plane wave we can define by electric field EI, E0I is a constant and it has a vector, and then phase factor k I dot r minus omega t. Of course, you are considering monochromatic wave, single frequency, monochromatic wave, monochromatic plane wave. Okay. So, it is making an incidence and corresponding magnetic field is this one. Similarly, I can represent transmitted wave electric field and magnetic field. Okay. Kt, it is defined by kt, in this case kt is the propagation vector, and it is kr, similarly we can consider reflected one. Okay. So far so good, we can see that okay, there will be some situation can occur and plane wave remain plane wave in the transmitted second medium, and plane wave will remain plane wave when it is getting reflected. If that type of linearity we have considered, both the medium we consider linear. Okay. Now, you see we have one more characteristics to define. One is eta 1, that is the characteristics impedance, that is nothing but you have to take the amplitude of the electric field and amplitude of the magnetic field. Normally they are, most of the time they are not in same direction, they are orthogonal. You take their ratio and that is the amplitude divided by amplitude, and that we have derived earlier in terms of frequency omega and conductivity sigma 1, permeability mu 1 and permittivity epsilon 1. Similarly, for second medium eta 2 is this one. Okay, fine. Now, we also know that what is kt and what is ki. Okay. Kt is actually 2 pi by lambda, it can be written as omega by c and n 2 plus j kappa 2. Because of this all these parameters are there, we know that refractive index normally we can represent square root of epsilon r. If it is a lossy medium or so, epsilon r normally we consider something like this. If it is omega frequency dependent, we write frequency dependent, and that is normally we represent as n real part of the refractive index and imaginary part of the refractive index called extinction ratio. Okay. So, kt will be 2 pi by lambda can be written as frequency by velocity of light c, and n 2, that means the real part of the refractive index in medium 2 and real imaginary part of the refractive index in medium 2. Similarly, ki and kr must be same because they are in the same medium 1. We can write here n 1. So, this can be written as n 1 omega complex refractive index n 1 plus j k 1 kappa 1. Okay. So, since ki and k are in the same medium, their absolute value would be same, that is what we have written here, and for kt we have written, only their direction is different and their value will be also different for kt and ki if you can compare. Fine. So, now we can consider, okay, let us concentrate little bit on our electric field vector. We know that we have already represented the wave vector, direction of the wave vectors for incident wave. This is incident wave, reflected wave and transmitted wave. We have represented already. Now, we know that this is plain electromagnetic wave associated with electric field and magnetic field. We have the liberty to consider a special case for understanding purpose, which is called TE polarization. We can call it as a TE polarization. Sometimes you can consider TE polarization. Sometimes it is called sigma polarization, sometimes it is called S polarization. If you have a S polarization, for that with this reference frame, we can consider electric field will have only oscillating along y direction, only y component will be there. So, electric field will be oscillating perpendicular to the screen and no x component, no z component of the electric field present. So, called electric field is in the, this is your E y in this direction perpendicular to the screen, then magnetic field can be perpendicular to the both k I vector as well as perpendicular to the electrical vector, electrical field E y. So, that means magnetic field, this one H can have the components, or H field can oscillate in x z plane, meaning H field will have x component and z component. So, if this is the situation, then absolutely fine, a plane wave can propagate along k I direction. So, if a wave, if an electromagnetic wave has a electric field component oscillating along y direction and magnetic field is oscillating in the x z plane, but both are perpendicular to the wave vector k I, then we can ensure that wave is propagating, energy can be carried in this direction. So far good. Similarly, we can consider another combination where this field, this electric field will be oscillating in the, this can be your electric field and this can be your, this is your electric field and this will be your magnetic field. Magnetic field will be in the y direction and electric field will be in the x z plane. So, I have written here x z plane electric field, E x component is there, E z component is there, y component missing and y component of magnetic field will be there, and that also another kind of situation you can assume, so that electromagnetic wave can carry energy in the k I direction. So, what we made confirm that if k I propagation direction is there, that means electric field and magnetic field can be perpendicular to the k I and their combination can be decomposed into T m polarization or T polarization. Any polarization, any direction electric field is oscillating perpendicular to the k I, you can decompose into these two different combination and you can treat them independently, and at the end you can just sum them what is the resultant effect. So, sometimes again likewise T polarization, T m polarization also sometimes it is called T m polarization of course, and sometimes it is called pi polarization and sometimes it is called what do you call that pi p polarization. So, this is sometimes S polarization, sigma polarization. So, that way different textbook normally they define like that. So, we can consider two different type of polarization for our understanding purpose, for our analysis purpose. The actual reason to consider this type of components, set of components, all the 6 components can have any electromagnetic wave propagating in k I direction, all the 6 components can have, okay, but out of these 6 components I can ensure that okay, these 3 components E y component, H x component, E y and H x, H z, these 3 component is good enough. Another set you can consider E x, E z and H y component good enough to ensure energy propagation in this direction. You can independently think T polarization, T m polarization. As I mentioned, the reason, actual reason to consider that thing is that to utilize the boundary condition. What is that? boundary conditions according to our Maxwell's equation, Gauss law, etc., we can derive a set of boundary conditions. That is, you know how to derive that in basic electromagnetic book. You can find that normal component of displacement vector. You know, displacement is nothing but displacement vector is epsilon E. So, if you see displacement vector, if wave propagating from medium 1 and it has some part is medium 2 and something reflected back here. So, you can see that exactly you just consider x equal to say 0 minus coordinate and x equal to 0 plus coordinate. These two coordinate point just above the interface and just below the interface. If we just compare, for example, here exactly at O, if I consider x 0 plus and x 0 minus, I can find out what is the total displacement vector in medium 1 and I can find out what is the total displacement vector in medium 2. When I say the total displacement vector in medium 1, that means I have to consider incident wave as well as reflected wave, their resultant. So, their sum of their this displacement vector, you take the normal component and normal component in the second medium displacement vector. Normally, they are continuous. Okay. So, that is one boundary condition we can. That means, normal component means that is normal to the yz plane. If we have a component of displacement vector normal to the yz plane in medium 1 and medium 2 exactly at x 0 plus 1 and x 0 minus 1, they must be equal. Normally, they can be some value if in the interface there is a charge available. We are considering there is no charge in the interface. So, we can consider that. And if you see the tangential component of the electric field, tangential component of the electric field in medium 1 and tangential component of the medium 2, they must be also equal, E1t and E2t. E1t in medium 1, I have to consider electric field, total electric field of incident wave and total electric field of reflected wave, and medium 2 only transmitted wave. So, they should be also continuous. Similarly, for magnetic field, normal component and tangential component when there is no current flowing across the interface. So, if we just use these two we want to use these two boundary condition, it would be easier if I have electric field only Ey component, meaning that is the exactly tangential component in the interface, and for TM polarization only component magnetic field Hy, that is tangential component to the interface. So, it would be easier to analyze all the waves reflected and transmitted wave, how they behave, how much fraction it will be reflected, how much fraction will be transmitted, that will be easily can be derived. Okay. So, this is the main reason of considering the TE type and TM type things, so that you can treat them independently. You have to use the boundary condition, and using this boundary condition, one more important thing you could find out here, Kij, that means Kij, if I have a theta I, Kij equal to Ki, so called theta I, this one is theta I, so this is 90 minus theta, so Ki sin theta. Sin theta I, Kij equal to sin theta I, and similarly if I just try to find out Krz is nothing but Kr sin theta r, and if I just find Ktz z direction, this component Kt sin theta t. So, these are actually we are assuming that is the tangential component of the wave vector in incident wave, this one, reflected wave, this one, and tangential component of the transmitted wave, this one. According to the boundary condition, they must be equal. All are of equal amplitude, that is actually boundary condition MCOs. But you can see that overall Kt vector, Kr vector, they are in different direction compared to Ki, if you compare with this one. Why that happened? That happened because of the Kix component and Krx component and Ktx component, they differ, normal component of the wave vector they differ. So, because of the normal component differs, so that this is Ktx, Ktz and Ktx, if it is their variation is different. So, you can think of that, okay, their angle will be different. So, that is the reason the reflected wave, transmitted wave, they can occur differently, their angle can be different. Okay, good, so far so good. So, we have defined that electromagnetic wave, plane electromagnetic wave in the interface of two medium, what can happen, mathematical setup already established now. Then what we should think now? Next thing is that, well, we just again fix that either we are considering TE polarization and TM polarization I just mentioned here. All the things are refreshed here now. Okay. So, all the parameters we know where from they are coming, how to derive that must be known to you. Now, using the boundary condition, I can find out for TE polarization that what is the reflected amplitude coming here and what is the incident electromagnetic wave amplitude. If you take the ratio reflection by incident, that will be called as a reflection coefficient, amplitude reflection coefficient. We call it as a gamma TE, because TE polarization, if we just consider TE polarization will have certain boundary condition, Ui is the tangential component. Using that, we can find what is the reflection coefficient for TE polarization. Similarly, utilizing the boundary condition, that is a few steps you can do, any electromagnetic textbook you can find those things. So, here also for TM polarization I can find this thing. You see, if you just compare, they are almost identical looking, only thing is that theta I and theta t, they are interchanged. In the first term theta u was there and here first term is theta t, theta t, theta I. Otherwise, numerator denominator you see they are same, plus minus only. So, reflection coefficient for TE polarization and for TM polarization we can derive in terms of characteristics impedance, so called intrinsic impedance of the medium, two media, eta 1 and eta 2, and they are of course theta dependent, theta I dependent. Obviously, these are actually first time derived by using boundary condition, it is Fresnel. So, that is why they are called as a Fresnel equation, Fresnel's law of reflection or Fresnel's equation for reflection. Obviously, you can find out if theta equal to so called 0 degree normal incidence, suppose this theta is normal incidence. So, theta t also will be 0, theta r will be same direction, it will be reflected, all will be 0. In that case, for normal incidence theta I equal to 0, then this reflection coefficient will come eta 2 minus eta 1 divided by eta 2 plus eta 1, and here also eta 2 minus eta 1 divided by eta 2 plus eta 1. So, they are identical. Both the polarization for normal incidence, their reflection coefficient is same. This one and this one same for normal incidence. Only they will differ if they are making an incident with an angle. And if it is angle, if you see theta t here and theta I, that way you can just try to. So, TE polarization, TM polarization can see different type of reflection coefficient. Fine. Now, reflection coefficient is there. If I am considering that yz plane in the interface, nothing is being lost, absorbed, no absorption loss, nothing is happening. In that case, we can find out what is the energy is conserved. In that case, we can see that how much energy, how much transmission is there, transmission coefficient. Transmission coefficient means this transmission coefficient I can say that it is nothing but E0t by E0i. Transmission coefficient for T polarization, it is simple. If you know the reflection coefficient, you add 1, then it will be transmission coefficient. That is also can be derived from the that boundary conditions. Okay. Similarly, for TM polarization, it is same, but apart from that, you have to multiply for the transmission coefficient cos theta t by cos theta I. Again, if theta t and theta I equal to 0, theta t equal to 0, theta equal to 0, that is 1. So, it will be for normal incidence, they are same basically. Only if it is angle is different, then only your transmission also will be different. Okay. So, now, so we know that how much fraction of amplitude is transmitting, how much fraction of amplitude will be reflecting. So, if you have both mixture of T and TM polarization, you will see one of the polarization will be reflecting more and another will be reflecting less, depending on the angle, as long as this angle is not 0 normal incident. Okay. So, now little bit move on. Special case, I have just moved eta 2 is same thing I have written here, eta 1 here, and special case we are considering. What we are considering? We are considering that first medium is a dielectric medium. So, it is a lossless sigma 1 equal to 0 if I consider, and it is a non-magnetic material mu 1 equal to mu 0, that means mu r equal to 1, non-magnetic material. Permittivity is there, permittivity epsilon 1, you can say right epsilon 0 epsilon 1 r, that is there. So, it is a dielectric medium. If you just insert all these in this equation, then you will get eta 1 equal to eta naught by n 1, where n 1 is equal to square root of epsilon 1 r. Dielectric constant square root if you take, that is the refractive index, that is actually called refractive index. That means, I can characterize medium 1, if it is dielectric, I can just represent eta value is eta naught by n 1. So, if you know refractive index, then characteristics impedance you can just factor it, then you can get the impedance, okay, eta naught by eta 1. And medium 2 slightly, it is completely different. Instead of sigma 1 equal to tends to 0, we consider sigma 2 tends to infinity, very large value, high conductivity, it is a metal. That means, I am considering medium 1 equal to dielectric and medium 2 is a metal. What happens for that? And also non-magnetic, metals are mostly non-magnetic. So, mu 2 equal to 0. So, mu r also here we are putting 0, and epsilon 2 we can just write again epsilon 0 epsilon 2 r fine. Okay. So far so good. Now, if you just put, I know that in this case eta 2 will be equal to, if you just put here sigma to infinity, that means eta 2 tends to 0, something divided by very large value. So, eta 2 tends to 0 I have written. So, eta 2 tends to 0, if we are putting 0 here, 0 here, 0 here, 0 here, both the polarization. What happens? Then gamma t will be what? Gamma t will be equal to, you can write gamma t will be equal to minus 1, because that one will be 0. So, eta 1 minus 1, and here that is also gamma T m will be minus 1. That means, reflection coefficient, when it reflects both for TE polarization and TM polarization, the reflection coefficient inverse, that means completely reflected with minus sign, that means pi phase shift. You are introducing pi phase shift upon reflection, both the polarization T and TM. So, if first medium is the dielectric medium and second medium, your wave is coming from a dielectric, homogeneous dielectric medium, and then you have an interface of metal. This is for example say metal. Then what happens? For any angle, theta I can be anything, your wave will be completely reflected and it will be phased, pi phase shift will be observed. So, this is the beauty. I have not considered any frequency here, whether low frequency, large frequency or whatever, some arbitrary frequency. As long as you consider at that particular frequency sigma 1 equal to 0 and sigma 2 equal to infinity for the second media, then all the frequency to be reflected back. So, it can happen for microwave waveguide also, and it can happen also for the optical frequencies also, microwave frequency as well as optical frequency. This is valid if you can find a metal where sigma conductivity is very large, and you can find a dielectric where conductivity is absolutely almost near to 0. So, that type of situation if it is there, then the electromagnetic wave can be reflected with pi phase shift, both lower frequency as well as higher frequency. Only consideration is that conductivity. the frequency you are considering, at that particular frequency the conductivity should be large in the metal and very low towards 0 in the dielectric, then it will reflect. So, I say that reflectivity nearly 100% and phase shift is pi. That is why I have not shown any reflected wave, rather I show little bit here. What is that? That you know what is that, because metal, if you have some kind of incident electromagnetic wave, metal normally because of the high conductivity, you know, it cannot propagate, it normally attenuates. So, this attenuation, you know, up to the skin depth it can attenuate, and then skin depth I can just derived earlier already. This is delta, if you know frequency, 2 by frequency and conductivity, some conductivity will be there, it is large, but whatever value is there you can put down mu 0, that thing you get the bit, it will be penetrated. So, if you just little bit simplify here, it is proportional to square root of lambda. What does it mean? Square root of lambda means inversely proportional to frequency. Of course, omega is the inversely proportional square root of frequency, that is the thing. So, when lambda increases, then this delta will be increasing, skin depth, it will be penetrating more inside the material. But when lambda is small, frequency is high towards optical frequency, then this delta will be almost 0, nothing will be there inside, little bit will be going inside. So, for lambda penetrating more, you can imagine that when it penetrates a little more, there can be some kind of heating effect, some kind of resistive loss, attenuation, because of the attenuation some loss will be there. But when very large sigma and very high frequency, this delta will be less, so it will be less penetrating, so loss will be less. So, you can consider almost 100% reflectivity for optical frequency. Microwave frequency also you can see that okay, loss is very minimal. So, if this is the case, for microwave particularly, we use microwave waveguide. If you are using a 2 metal plate, one metal plate here at x equal to d, another metal plate at x equal to 0, then any wave comes here for any angle, this is a metal, this is metal, and inside you have a dielectric medium, just consider a dielectric medium with this definition. So, this metal and this metal may be identical metal plate you are considering, which is parallel to the yz plane, perpendicular to the x axis, and you can make their separation as d. This is the d separation you can consider. Then any wave, any angle you come, that will reflect completely, come back and goes like this. It can happen little bit, it can be some lossy, it can happen that okay 99.999% maybe it will be reflected, little bit will be lost. So, that is the principle used for microwave waveguide. This is one dimension, you can make like a box, okay. Inside the box you can actually launch microwave signal, then it will be going back and forth reflection and it will be propagating. That is the basic principle, because metal reflects electromagnetic wave. So, that is why you can design waveguide also, dielectric inside, and you can make a box, that is a microwave waveguide. So, now my question is that what is the problem if we use same thing for optical waveguide, for optical interconnect? That is the important question now I want to discuss. Just think about that. Okay. Let us consider like this, that wave vector, this is k1 wave vector coming, and you know that this is k1x dielectric material medium. So, that is the x component, that is the z component, and when it reflects back x component, that is the z component. And we know that this k1z they are normally same, and k1x is just inverted. Okay. And we know here reflection will be there, some value reflection, this gamma can be 99.999% or maybe 0.99959 you can put gamma value, and you have e to the power j pi phase shift will be there. Same thing will happen here, and repeatedly it go back and forth reflection, it should happen like that. And this here whatever it will be penetrating in the skin depth, and you can imagine that something in the x direction completely it is imaginary, and that is why it attenuates up to the skin depth. That is clear. All right. Now, you see you can actually decompose when wave propagating in this direction and coming back this direction. You can see only k1 x, if you just consider k1 x you are considering, they are actually counter propagating wave component. Okay. So, if this reflection is not the only condition for guidance, one more thing you have to consider, that this wave component propagating vertical direction, after a round trip travel, it should complete 2 pi phase shift, 2 pi times integer. So, what is the phase shift? k1 x, if it is a wave component propagating in this direction, some component wave vector component is this one. So, round trip means d and coming back d. So, 2d. So, normally you know wave vector multiplied by L, that is actually phase, round trip phase. So, round trip means 2d times k1 x we multiply, that is the phase, round trip phase. Round trip phase, if it is 2 pi times m integer, m equal to 1, 2, 3, 4, so on, then this round trip phase can cause certain kind of mode solution. It actually ensures that round trip k1 x component actually creating certain kind of standing wave in the lateral direction, x direction, and that standing wave depending on k1 x value you can consider one mode. So, from here you can actually find out what is the k1 x. It is a microwave waveguide, these are actually you have learned earlier if you have studied any electromagnetic theory course. So, then from this equation you get k1 x equal to m pi by d. So, that means k1 x, this x component will be discretized based on m equal to 1, 2, 3, 4, so on, and depending on the d value. D is the separation, that is I am just considering 1D confinement here, 1D mode. Now, you know you have this condition k1 x square, k1 z square, that should be equal to k1 square, right, wave vector. So, k1 z must be k2 z, even if it is some field is in the skin depth, that is k2 z is present, they should be equal, tangential component wave vector, they should be equal, we define that as a beta. Okay. Now, we can say that k1 x square plus beta square equal to k1 is omega by c n1 square. Now, from here I can write beta value. So, this one I can write beta square equal to omega by c n1 square minus k1 x square. So, this k1 x square I know this one k1 x square. So, I can write beta m square equal to this one. So, since k1 x is discretized for a certain mode, I can find that that mode we will have longitudinal propagation constant k2 z, k1 z, that will be also discretized depending on the m equal to 1, 2, so on. So, we have written down like this, n is the refractive index n1 here. So, that means this k1 z also discretized, k1 x is also discretized to have a standing wave pattern along lateral direction, x direction, fine. Now, you see then any wave, that mode can be expressed, mode propagating along z direction can be expressed that if it is a just T polarization, only Uy component present, then I can say that Ay component E0, and standing wave I can define like this, sin m pi d x. So, x equal to 0, value will be 0, x equal to d, that value m pi, that will be equal to 0, m equal to 1, 2, 3, 4, so on, different type of modes you can have, and corresponding mode we can have, that mode will have longitudinal component beta m, that is defined by this equation. So, this is your propagating mode. Along with that, we just added one more part, e to the power minus alpha z, that is basically as it propagates it will suffer certain kind of loss. Where from that loss comes? Because every reflection you see it is a metal interaction, some loss will be there. So, that is why you can see some kind of little bit of losses will be there. So, that you have to count for. The loss is very important. For microwave, normally if this wave is considered as a optical wave where lambda is very small, okay, we can consider for typical example, okay, we consider say gamma equal to this one and gamma square will be this one, that is reflectivity, little bit loss is there in optical domain for example. And if we consider this theta equal to say 45 degree, and for a mode m equal to 1, I am considering here 1, and optical wavelength is the third communication window, optical communication window 1550 nanometer, 1.55 micrometer I consider. And if you consider this is a Si2, just silicon dioxide, then silicon dioxide at that particular wavelength diffractive index is around 1.55, 1.45. So, this is your metal, this side is metal and this is metal for example. I am just considering if I consider optical wave whether this can be useful for waveguide, and that can be also this type of mode can be there or not, that is the understanding. So, now we see that n1 given, lambda given, m1 I am considering 1 for fundamental mode for example, m equal to 1, theta 45 degree. Then what we get? We get this value k1x. What is the k1x? k1x will be k1 times cos 45 degree. So, k1x, x component will be k1 cosine 45 degree, and k1 equal to 2 pi by lambda n1 propagation vector cosine 45 degree. That k1x if m equal to 1 you are putting, that will be pi by d. So, k1x means 2 pi by lambda n1 cos 45 degree and m equal to 1 pi by d. This gives you all the value lambda and n1 cos 45 degree value you put, then d value comes 750 nanometer. So, if you are interested to use optical waveguide, metal optical waveguide, the thickness of the waveguide, this thickness, this should be in the order of 1 micron or 750 nanometer depending on the wavelength. Fundamental mode if you are just confining in that direction, 750 nanometer. Now, suppose you can 750 nanometer and metal plate in between 750 nanometer oxide you can actually design without any problem, that is fine. But what happens? Let us consider that how many reflection required to travel 1 millimeter of length. You want to design 1 millimeter such waveguide, optical waveguide. I would like to understand how many number of total internal reflection, it is not total internal reflection taking place in everywhere there. Suppose if it travels this length, then it is one reflection, another length, one more reflection, one length, one more reflection. So, one reflection how much length it travels along the waveguide? This is 45 degree and this is 750 nanometer d. So, this also will be 750 nanometer. So, that means for 750 nanometer travel it needs one reflection, and for 1 millimeter means 10 to the power 6 nanometer. 10 to the power 6 nanometer divided by 750 nanometer. This is also nanometer, 1 millimeter, and then this is also nanometer. So, you need at least 1333, just simple calculation it gives you 1333 reflections required just to travel 1 millimeter. And if you are considering every reflection it contributes 0.99 reflectivity. This many number of reflection if it is happening, so what would be the loss factor? So, loss factor will be this power, if it is gamma square means power loss factor, power is gamma square equal to 0.98 gamma square to the power n. Okay. If I just consider gamma equal to 0.99, gamma square means power reflection coefficient is 0.98 and n reflection happens, every reflection you get 0.98 factor. So, 0.98 multiplied by this many number of to the power 1333, that gives you very small number 2.31 10 to the power minus 12. Okay. So, basically this value actually gives equivalent to about 116 dB loss per millimeter. You imagine if you can design your so-called metal optical waveguide, but you have to afford this much loss. It's very difficult. You want to use this as a optical interconnect. So, this is impractical, completely impractical, but this is very good for microwave. You know, microwave, you are considering maybe wavelength in the order of 1 centimeter. So, 1 centimeter you want to travel few centimeter length, you can have a few reflections only few reflection, you do not have much losses. Whenever you are considering optical frequency, your dimension is scaled down. Once the dimension scaled down, number of reflections will be more and more reflections, and more reflection means each time you are contributing the loss factor. So, ultimately you will be getting very less amount output. Okay. So, this is heavily lost. So, that this is not really possible to have your optical waveguide. Metal waveguides are completely not suitable. So, what is the solution? So, solution is that we have to rely on total internal reflection. Instead of metal, we have to find out new type of things. What is the optical fiber, you know, all those type of things. So, that is why we have to go for really dielectric waveguide, where light higher frequency can undergo some kind of total internal reflection for a certain angle. That angle must be greater than critical angle. So, we can have a layer 1D planar waveguide, one higher refractive index N1, and then substrate can have a lower refractive index, and top can be another refractive index dielectric. All are dielectric, 3 layers of dielectric. Then N1, if it is greater than both N2 and N3, then any light coming in, it can undergo some kind of total internal reflection for a certain angle, if it is incident angle is more than critical angle. So, reflection. So, you can have the mode will be like this. Mode can be guided along z direction with a propagation constant beta m, similar to electromagnetic microwave whatever we have considered, and field will be confined along x direction because of the total internal reflection. And if you can create this type of structure, you can have 2D photonic wire waveguide. So, you can have total internal reflection in 2 dimension, both x axis as well as in y axis, x direction as well as y direction. So, in that case, you can have a field distribution confined in xy plane. Well defined shape you will be getting as a mode, and that mode will be propagating like this. Okay. So, this type of waveguide normally we are looking forward to design optical interconnect in silicon or in anywhere. Silicon on insulator, for example. This is the silicon on insulator commercially available, 300 millimeter. It is a 3-layer system. This is called substrate, 700 micrometer thickness, 500 to 700 micrometer normal typical thickness substrate for handling purpose. Then you have a box, basically silicon dioxide. It can happen 1 to 3 micrometer thickness, and then top layer in the order of say 200 nanometer or more, less also, more or less it can happen. This type of wafers are available. If you take a particular square shape of the wafer, then you can just lateral vertically you can see box layer, substrate, silicon, and SOI. This is basically actually silicon, thin layer of silicon will be there. And if you etch like this, then your silicon dioxide here refractive index is around 1.45, and outside is air, it is refractive index is 1, and silicon refractive index is 3.47. So, you can actually design a waveguide, photonic wire waveguide, and air can be replaced by another silicon dioxide cladding, and you can have all the CMOS technology, different type of metal layers for reconfigurable structures, etc., for biasing purpose, etc., all those type of thing. 2 different type of waveguide structures normally we will be using for optical interconnects. So, now next our objective is to understand how to design this single mode waveguide or multi-mode waveguide or certain waveguide property for special applications. That will be in the next lecture I will be discussing. Thank you very much.